Now to introduce today's speaker, Kristy Stevenson. Kristy, I'm just passing the screen to you if you can accept the invitation to present. Now, Kristy is a research associate from the School of Biology and Environmental Science at the Queensland University of Technology. She will be presenting some early research into the attributes of forest communities that may make them more vulnerable to myrtle rust impacts. Kristy, if you're all good there, feel free to get underway.
Okay, cool. So hi everyone, my name's Kristy. So I'm presenting today on behalf of all the authors listed here who've each contributed to this project, which is part of the National Environmental Science Program in Australia within the Resilient Landscapes Hub. So I'd like to begin by acknowledging the traditional owners of the lands on which this research was conducted, the Kumaberi, Tulging and Turrbal and Yagara peoples. I'd like to pay our respects to their elders, laws, customs and creation spirits, and to recognise that these lands have always been places of learning, teaching and research. This is coming from an Australian background, so forgive me if I miss anything, but so in Australia anyway, we've got growing data on the impacts of myrtle rust on several individual species that have been pretty heavily impacted, such as Rhyndamnia rubescens and Rhyndamnia maydeniana, both of which are pictured here, which are now listed as critically endangered in part due to myrtle rust. But we have more limited data on the impacts of myrtle rust at the plant community level, which is where this project fits. And it builds on research that observed some wet sclerophyll patches that contained a high proportion of rainforest Myrtaceae have been badly impacted by myrtle rust. But first, a bit of background on what wet sclerophyll forests are. So I love this diagram here, which kind of shows where wet sclerophyll forests fit. So you kind of got rainforest at one side of the spectrum, and then like more dry sclerophyll forests, so a more open eucalypt canopy with a kind of grassy understory at the other extreme, and wet sclerophyll forest fits in the middle. So it's got a eucalypt canopy and a really variable understory ranging from like dense rainforest through to more open grassy communities. And the composition and structure is dependent on the type of disturbance it experiences and the frequency of disturbance. So yeah, they're well adapted to disturbance, they're very transitional and they're highly variable forests. Myrtaceae species are present in these forests in the canopy as the eucalypts, but they're also present in the midstory and understory as rainforest trees. And it's these rainforest trees that we're interested in, as they're the ones that have the susceptibility to myrtle rust. When we look to the literature to see, well, how common are these forest patches that contain a high density of rainforest Myrtaceae, we found there was actually pretty limited published data available on these forests from the subtropics, which is where we're conducting this study. So a byproduct of this, we're also gathering more data on them. So what might some of the drivers be then of these highly dense patches? Well, we know that several of the species that are highly susceptible to myrtle rust, such as these two rainforest trees, Archaeodomatus becklerii and Rhyndamnia rubescens, pictured here, can act as early colonizers and have the capacity to resprout from basal buds. So it's possible that differences in forest management and land clearing may select for species with these traits. So our first research aim was to investigate if current land tenure or historic land clearing correlated with myrtle rust impacts. This is a slightly longer bow, but this paper by Island and Pegg highlighted that elevated levels of inoculum increase the severity of myrtle rust symptoms under glasshouse conditions. So we were kind of wondering if we might see that in the field, if the density of susceptible host trees as kind of a proxy for potential inoculum load might correlate with disease impact level. So I mentioned already, we have these few patches that were dominated by rainforest Myrtaceae. They're all from a single forest community. So under the Queensland system, it's a single regional ecosystem, 12-11-2, if you're familiar with that framework, but it's dominated by some eucalypt species, Eucalyptus saligna, Eucalyptus grandis, Eucalyptus microcories, and the Phostomene confertus with a vine forest or rainforest understory. And this community supports 4 rainforest Myrtaceae of differing levels of susceptibility to myrtle rust. So they're pictured here. Archaeotomyrta speculari at the top, highly susceptible to myrtle rust. Below, Rhodamni rubescens, highly to extremely susceptible to myrtle rust. Palladiostigma glabrum, relatively tolerant to moderately susceptible to myrtle rust. And Syzygium oleosum, relatively tolerant to highly susceptible to myrtle rust. So our sites were all in the Gold Coast hinterland, so about an hour and a half south of Brisbane, I can see on the map there, and across these 3 neighbouring valleys. So it's likely we're going to have 6 more sites. So this is just data from our initial sites. But yeah, at this stage, they're in these 3 neighbouring valleys. Our initial design was based on current land tenure, which is shown in the colour of the dots. So yellow being national park, blue being privately owned, and pink being council owned. So you can see they're relatively well spread across the valleys. This is an example from just one of the sites. So this is a section of one of the national parks. So we used this Queensland Globe, which is like an online platform map. It has different layers. So we use this to map out the patches of the forest type that we were interested in, which here is circled in white. And we had 3 50 by 2 metre transect lines. We started one end of each of the transects on an edge. So in this case, it was a gravel road, but we also had like bitumen roads, walking tracks, but heading into a less disturbed area. Because we were interested in the understory and mid-story trees, we had a size threshold. So trees that were taller than 1 metre that had a diameter at 50 centimetres of less than 10 centimetres. And we identified all these trees to the species level. We also scored each of the rainforest Myrtaceae for Myrtle Rust impacts using this paper by Fencham et al. So this is an example using Archaeotomyrta speculari. So the tree that's on the outside would get the highest disease score, as it had 100% canopy dieback, but it was re-sprouting from the base, while the tree in the middle would get a very low mean disease score because it's got very minimal branch dieback. So onto our results. So we saw pretty quickly there was no impact of current land tenure. Yeah, this may be unsurprising as these valleys have a long history of disturbance since colonisation. So they were first selectively logged for timber, primarily species red cedar, and then pretty extensively cleared for farming, primarily dairy and bananas. The valleys also differed in the extent of clearing. So the Currumbin Valley and the Tullabudgera Valley were pretty extensively cleared, especially along the creek line where it was quite flat. So you can see the pink dot that's circled here. It looks like it's pretty well surrounded by forest now in 2024, but if we look back to 1961, it's part of this really highly cleared and fragmented landscape. In contrast, the top of the Myrtaceae Valley, we can see it's quite hilly and quite steep, yeah, which is possibly why it wasn't cleared as extensively. And yeah, you can see in 1961, while there was some clearing, at least our sites that were sampled, so they're represented by the little rectangles, they were pretty well connected even in 1961. And I've moved the rectangle slightly, apologies about that. Yeah, so this difference in land clearing is possibly why we see the land use that we see today. So this map up the top can see all our sites again are marked by the different coloured circles. These boundaries represent a chain of conservation areas that are owned by different people, so national parks, council, and privately owned. Yeah, so it's possibly a reflection of lower land clearing in the past. And yeah, when we looked at species composition, we didn't see any impacts. We didn't see any impacts of land clearing, land tenure on species composition, but we did see it based on the valleys. So, and when we include these 2 circles, it actually proved the fit of our model. So this is an MDS plot. So each of the points are one of our transects. And yeah, the ellipses are 95% confidence intervals. So you can see the grouping out based on the valleys. Yeah, and also the tightness of the grouping also appears to relate to how fragmented and the dispersal of these sites spatially as well. And this was supported by a permanent analysis that we ran with site as a random effect. We also looked into the past for each of the sites individually. So yeah, 1961 was the earliest we could get data for all the sites. And you can see here with 2024 in the centre. So we had two different levels of past land clearing. So up the top is an example of Luxton Bush Reserve. So the rectangle is approximately where our sites were. And you can see in 1961, there were very few trees remaining at that site. In contrast to the bottom, which is that same site of the national park, which has pretty intact canopy in 1961. So that was classified as low historic land clearing. So we ran some linear mixed effects models with site as a random effect, and you can see that there was an impact of historic land clearing. We used a couple of metrics of Myrtle Rust impact. So the proportion of rainforest Myrtaceae is kind of an indicator of the vulnerability of that patch to Myrtle Rust, and also mean disease score. So that's kind of the extent of canopy dieback for the Myrtaceae trees within that transect. And yeah, you can see the proportion was higher in sites that had experienced historic land clearing, and also the trees that were present there had a higher mean dieback score. We also looked at the impacts of historic land clearing on species composition, but yeah, didn't see any impacts. As I've already highlighted, I think that's due to the spatial arrangement and potentially the past fragmentation. But we did look also at just the composition of the rainforest Myrtaceae. So the 10 species that we observed, unfortunately, they weren't present in all the transects, so we ended up collapsing the data down. So you can just see the 15 sites represented here, and acknowledging there is an imbalance, as our initial design was based on current land tenure rather than historic land clearing. But you can see in the NMDS they are grouping out, and this was supported when we tested it statistically using a permanent over analysis. We also ran a SIMPR analysis to see which of the species was driving this dissimilarity between the groups, and it was this rainforest tree, Archaeodomatus beckleri, which when we looked at our data was kind of unsurprising. These are 3 of the highly cleared sites here, and yeah, around 80% of the Archaeodomatus stems that we recorded were present at these 3 sites. We know this species is an early colonizer, it's highly susceptible to Myrtle Rust, and it's also frequent or dominant in multiple canopy layers of this regional ecosystem or this forest community. And we also know that it can resprout from basal buds, which may have been one mechanism that helped it to dominate and survive at these repeatedly cleared sites. But this resprouting characteristic, it's not actually unusual within Australian rainforest trees. So this review by Clark et al. Observed that the majority of rainforest trees that they looked at had a capacity to resprout, and 91% of them from basal buds. We looked at the 115 species that we recorded, looked into Austrates, which is a big database of traits. And yeah, of the 70% of our species that had a trait listed, for bud bank location, 86% of them could resprout basally. So yeah, resprouting, it's not an unusual response to damage in rainforest trees, to damage caused by herbivory, flooding, storms, fire, and also apparently to Myrtle Rust. And when we put this in like a global context, resprouting is also not unusual to damage caused by other invasive plant pathogens like chestnut blight and sudden oak death. In trees that already were known to have this capacity, it appears like these pathogens are also triggering it there. So yeah, while we don't know if these trees will survive resprouting, it seems to be helping them in the current moment to persist. Onto our second question, so about the correlation between susceptible hosts and their dieback levels. So we saw Myrtle Rust at all the sites we visited, but the impacts were pretty variable. So this is just one example using, again, Archaeodomatus beckleri, because it was the most commonly rainforest tree that we observed. And you can see that 66% of the stems we observed had the highest disease score, so 100% canopy dieback, but were resprouting. But you can see there was also pretty substantial variability both within and between the sites where we observed it. And we plotted this out. So these are linear mixed effects models, again, with site as a random effect. You can see there was a correlation, positive correlation. So yeah, as the proportion of rainforest Myrtaceae trees in a plot increased, so did the proportion of dead trees. And similarly, as the proportion of rainforest Myrtaceae increased, the level of dieback we observed also increased. So this correlation with inoculum load. So this photo here is from Luxton Bush Reserve, which I showed earlier on the maps. So this was our worst impacted site. So yeah, so around a third of the trees, living trees that we observed were Archaeodomertus beckleri. And when we extrapolated out the number of dead trees we observed to the hectare level, it was around 7,000 dead trees per hectare. So a lot of dead trees at this site. Also, Archaeodomertus was very dominant. And even if a small proportion of those trees were Archaeodomertus, you can imagine like the potential inoculum load when Myrtle Rust arrived would have been quite high. But it's likely to be more complex than just host density. Myrtle Rust has multiple hosts with differing levels of susceptibility and potentially differing capacities to pass on the disease, as been shown in the US with sudden oak death. So yeah, this is just a start, and yeah, further research needs to be conducted to really understand this pattern. But in summary, historic land clearing does appear to be a factor that's affecting the abundance of some susceptible rainforest Myrtaceae in this regional ecosystem, increasing the vulnerability of these patches to Myrtle Rust. Resprouting is a key trait expressed by many rainforest trees that appears to aid tree survival under multiple types of damage, including land clearing and Myrtle Rust, and that rainforest Myrtaceae density appears to positively correlate with Myrtle Rust impacts. So what does it mean for management? Well, potentially these patches with low historic land clearing and low host density could be targeted for germplasm and seed collection. If these trees have lower levels of dieback, they could be better candidates for germplasm collection, for example. That in the inverse, being patches that are regenerated after repeated land clearing could be targeted to potentially mitigate the impacts of Myrtle Rust. So potentially removing some of those dead trees to reduce the fuel load. And yeah, there's big talk of potentially reintroducing some of these species in the future once we've, with all these breeding programs that are underway. So potentially we could reintroduce some of those trees into patches that have a lower abundance of rainforest Myrtaceae to kind of increase their chance of survival. And yeah, if anyone has any questions, my email's there as well. Please do reach out. We'd love to hear from you. So thank you.
Thank you, Kristy. That was a really fascinating talk. I have done some work on resprouting trees in fire-prone ecosystems in South Africa, so I kept thinking about that and not necessarily linking it back to the New Zealand context, which I'm sure other people are thinking about at the same time. I'm happy to field questions from the audience. If you can just pop those into the chat. I will start with a question, which is, do you know if resprouting growth has a similar susceptibility to other new growth? You are muted, or it's not working. I'm not sure.
There we go. I think that's a really great question, and yeah, it's definitely a limitation because a lot of these surveys you're visiting the site once, so you know it's really hard to say like how regularly are the resprouts putting on new leaves, how regularly are they being pushed back, even is the same sprout that you're seeing in 6 months the same one that was there before. So yeah, I think there's definitely space to do some monitoring to see how long these sprouts are surviving, and yeah, how much they're actually growing to be producing those leaves that are susceptible to Myrtle Rust.
Yeah, interesting. I have other questions coming in. Is there a difference in disease with different tree heights?
Tree heights?
Yeah.
Yeah. So we did measure like the diameter of the trees. I haven't actually done that analysis yet. That would be really interesting. Thank you for a great suggestion. I will look into it and get back to you.
Yeah. Perfect. And how do you protect trees that are resprouting? Are there management strategies available for resprouting trees specifically, do you think?
I mean, yeah, I think that's just the challenge that they're like stuck in one place with these spores flying around. So I mean, I guess it'd be the same as trying to protect like an adult tree in the field. I mean, there's like this vaccine that they've been developing, you know, but I think, yeah, for me anyway, in the field, the density aspect really stood out to me. Yeah, like some of the trees that we saw, you'd see just one tree, like Myrtaceae, in a big patch of other non-susceptible trees, and like looking reasonably happy. So, I mean, I guess that could be a way to protect trees that you're planting. Yeah, but in terms of like protecting one that's just, yeah, in its own community and can't be moved, I think, yeah, we're still working on how to figure that out. Yeah, but there's definitely people working on things like the vaccine and yeah, other mechanisms. Yeah.
Interesting. And then did you find higher disease incidence in less disturbed areas?
In less disturbed areas. So yeah. I mean, so that was the mean dieback score. So yeah, it looked like, I think because it was being driven, it looks like primarily by this one species that was really dominant, Archaeodomertus beckleri. So yeah, it was looking like so because of the metric that we were using, which was based on like the extent of canopy dieback, so we had like 4 different categories. So it was like 0 to 10% dieback, you know, 10 to 50%, 50 to 90%, and then 90 to 100, and then completely dead canopy and resprouting. So yeah, in that way, like these sites that had the higher levels of dieback would have like a higher proportion of trees that were resprouting from the base. Yeah, I mean, we still saw resprouting trees at sites that had been less disturbed, but we also saw more trees that still had some canopy intact. So we weren't actually looking at the spores per se. We were looking at like, did we see spores or not? Yes or no, but we were more looking at the extent of the canopy dieback. So yeah, we weren't actually measuring like how much of the pathogen was present. Yeah, unfortunately, like I'm an ecologist, so that measuring of the pathogen itself is a bit beyond my capability. So yeah, we were just saying were the spores there or not.
Yeah, I know the question comes from one of our researchers who's worked on a project looking at the edge effect, where
yes,
like how and the expectation was that there would be more disease on the edge and less in the interior, but they found that microclimates within the forest actually created this kind of optimal humidity within the forest that created as much, if not more, disease in the forest, even though there wasn't necessarily dieback happening in the canopy. It was more the understory growth that was dying. So interesting, and interesting differences between the systems as well, for sure.
Yeah. No, and also because our edges, like the patches were quite different. Like as I hopefully demonstrated on the maps, you know, some of the sites we had to trek in, you know, for like half an hour or so into a forest. So there was still an edge being a walking track, but you know, the patch itself was within a larger patch of forest. So even the edge effects, you know, would be different between sites that were in the really highly fragmented landscape versus in the middle of a national park. So yeah, it'd be interesting to look at that.
Yeah, interesting. All right, well, that's it for today. Thanks again, Kristy, for your presentation. A video of today's webinar will be made available on the Beyond Myrtle Rust website in the next couple of days. It will also be emailed to everyone who registered. Our next webinar will be Wednesday, the 13th of November. It will be held for the first time at a different time. That's right, we are deviating from our usual 11 a.m. start to accommodate Shay Swanepoel, a PhD student at the University of Pretoria, South Africa. She will present on research she conducted into the molecular dialogue between Eucalyptus grandis and the Myrtle Rust pathogen Austropuccinia psidii. To accommodate the time difference with South Africa, the talk will be in the evening at 7 p.m. New Zealand time, or if you're in Brisbane and Sydney, 4 p.m. So hopefully, Australia, you can make it. Keep a lookout for that webinar invite next month. I sincerely hope to see you there despite the late time. Thanks, everyone. Harera, and see you next time.